Hello and welcome. This is going to be our lecture video on projectiles. Go ahead, get your notes out, the date at the top. Let's get started. So what is a projectile? Go ahead, write this down. It's any object which is allowed to move freely under the influence of gravity and gravity alone. It needs to be airborne to become a projectile. So an example would be something like a baseball or a basketball, or even a person if they're shot out of a cannon. So if we have a big cannon at a carnival and it shoots out a person, that person, for a very short amount of time, becomes a projectile. The only forces acting on them are gravity and air resistance, but we're going to ignore air resistance. For the rest of the semester, we're just always going to ignore the effect of air resistance. So what is not a projectile? So anything on the ground. So anything on the ground. And then anything in the air that has its own power. So something like an airplane or a rocket. They do not count as projectiles unless, maybe an example of a rocket, if it runs out of fuel and then just starts to fall or fly under the influence of just gravity, then it becomes a projectile. So with a rocket, unless it loses fuel, at that point it becomes a projectile. When we throw something, the moment we release it, it becomes a projectile, but it can't have something that powers it and helps it fly. So like a drone is not a projectile because it has its own power. All of the movement of projectile comes from the initial moment when it is thrown or hit or launched or whatever. So when a projectile is launched, it typically follows a really nice mathematical shape that we call a parabola. So let's imagine that I hit a golf ball and I have a really nice golf shot. It goes nice and high, comes back down, lands on the green. This is a parabola. And it is symmetrical. Really important that these are symmetrical. One of the consequences of this being symmetrical is the speed on the way up exactly matches the speed on the way down. So right at this moment here, my golf ball is going to have some upward speed. Well, if I just draw a horizontal line to that moment on its way back down, it's going to have the exact same speed. The velocity might be in a different direction, but the speed should be the exact same. And then right at the very top, we could still be moving. We could still have horizontal velocity, but right at the top, we have no vertical velocity. But you can still be moving forward on this parabolic arc. So for our frame of reference, we're going to view every projectile from a 90-degree viewpoint. So we want to zoom out and stand 90 degrees to the movement. So I would, if I'm watching somebody hit a golf ball, I'd go way to the side of the driving range and watch them hit it. And then we're going to designate up and right to be the positive directions. And then down and left will be negative directions. And this object's moving in 2 dimensions. We can pick any moment and give that velocity a vector. That vector is going to have an angle, and we want to measure our angles in a 360-degree system. So things moving to the right will be moving at 0 degrees, moving straight up will be 90 degrees. To the left will be 180 degrees, straight down will be 270 degrees. And then if we come full circle, we're back to 0/360. So right at 360 is where it resets. We would never say 360, we would go to 359 and then reset to 0. All right, let's start getting into some practice problems. Here we have one about a horizontally launched projectile. If I throw a rock with a velocity of 3 meters per second and it hits the water 4.5 meters away from the cliff, how tall is the cliff? So let's go ahead and draw a diagram of this. We're going to zoom out and view it from a sideways view. Here's our rock. It's being launched straight out, and then gravity is starting to take over and pull it down to hit the water. So that's sort of half of a parabola. We just have the descending half of this parabola. Now, we don't know how tall this cliff is, but we do know that we're making a splash 4.5 meters away. And we started with an initial velocity of 3 meters per second. So one thing we're going to do is figure out, using a very basic kinematic equation, distance equals speed times time, how long this rock is in the air. Well, it traveled a total of 4.5 meters at a speed of 3 meters per second. Now that is only its horizontal distance, but this was only its horizontal speed. And the horizontal speed is not changing at all. Gravity does not affect things that are horizontal to it. So in a frictionless system, this rock would continue to move to the right at 3 meters per second forever. And we know that it hits the water 4.5 meters away. So it's traveled 4.5 meters purely horizontally. All right, so let's divide both sides by 3. 4.5 divided by 3 is going to be 1.5 seconds equals our time. Notice I ignore the units because I'm doing everything in meters and seconds, so I don't have to keep writing them. All right, so now I know the time. Now that I know the time, I can start focusing on the vertical movement. So purely vertically, we start with an initial velocity of 0 meters per second. You might say, well, I thought this says we start with an initial velocity of 3 meters per second, but that's because that's pointing straight sideways. That's all horizontal and no vertical. So the vertical velocity of this rock is 0 meters per second. Now the time it has to fall is 1.5 seconds. We just found that over here. And the acceleration is 9.8 meters per second. Technically, it's negative 9.8 meters per second, but it's not going to change this to treat it like a positive 9.8 meters per second. And so that's enough information to now solve for distance. Distance is question mark. All right, so I need a kinematic equation that relates these 4 variables. That kinematic equation is distance equals initial velocity times time, which initial velocity is 0, so this term will go away, plus 1/2 AT squared. And I've got all of that information, so distance equals 1/2 times 9.8 times 1.5 squared. Distance equals, and I'll plug that whole thing into my calculator, and I get 11.025 meters. So that is how tall this cliff is. 11.025 meters. All right, let's try another one of these. So let's imagine I drop a bag of gold coins from an airplane traveling 210 meters per second from a height of 8,000 meters. How fast would the bag be going on impact? So can we calculate the impact velocity? So one thing is this 210 meters per second, we can just store this. That is our horizontal velocity, and it's never going to change. As long as there's no air resistance, 210 meters per second is going to stay consistent. The only thing I need to figure out now is what is the vertical velocity going to be? So let's see if we can find the vertical velocity. So the only things I know is that we're going to fall a distance of 8,000 meters. The acceleration due to gravity is going to be 9.8, and we're starting with an initial vertical velocity of 0. Can I now find the final velocity? So I'm going to look through my kinematic equations for the one that doesn't have time, because that's the variable we don't have but don't care about. And I'll see that v final squared equals v initial squared plus 2ad. Now let's plug everything in. With 0 initial velocity, this term goes away, and we just get v final squared equals 2 times 9.8 times 8,000. Plug all that into my calculator. I get v final squared equals 156,800. Take the square root. I get 396. We'll round a little bit there. 396 meters per second vertical velocity. So now we got to put these together to figure out what the net velocity is. So at that moment of impact, we are moving vertically 393 or 96 meters per second, and we are moving horizontally 210 meters per second. So we have a vector pointing down, and we've got a vector pointing to the right. I've just added them together so that we can make this right triangle, and then solve for the resulting vector. It goes like this. All right, this looks like a Pythagorean theorem problem. 396 squared plus 210 squared equals c squared. I'll plug that whole thing in and then take the square root of both sides. Let me see what I get. So square root 396 squared plus 210 squared is 448 meters per second. Now, a bag of gold coins is going to be very dense. Therefore, air resistance won't have a huge impact. It would be very believable that this thing could be moving on the order of, 600-700 miles per hour when it hits the ground. So very fast if you drop a bag of gold coins out of an airplane while it's moving. All right, let's start talking about projectiles that are launched at an angle. What we want to do is immediately draw the angle of the vector with its magnitude, which is how fast it's going, then break it down into a right triangle so we can split that vector apart into its components. We want to know purely horizontal and purely vertical movement, and then only deal with those one at a time. So if this is vector v, its horizontal component would be called v sub x, and its vertical component would be called v sub y. And we can solve them using just a little bit of trig and this angle theta, which is measured off of the horizontal. So to find the length of v sub x, that is the adjacent, so we're going to want to use cosine. So it's going to be v times the cosine of theta equals v sub x. And then to find v sub y, we're going to use sine. So v times the sine of theta equals v sub y. All right, these are the components that we break every diagonal vector into. Components. All right, now for another word problem. A daredevil is shot out of a cannon at an angle of 45 degrees with an initial speed of 25 meters per second. The net is placed 50 meters away from the cannon. How high up on the net will the daredevil hit? Ignore air resistance. So here is that initial moment. We are launched at 45 degrees from horizontal with a velocity of 25 meters per second. Right away, we break that down into its components. All right, we want to figure out purely horizontal, purely vertical movement. So we're going to use those trig functions. 25 times the sine of 45. That's going to give us v sub y. And then 25 times the cosine of 45. That'll give us the purely horizontal component. Plug these in, and I think you'll notice something interesting is that they're the same number. Well, if this is a 45-degree angle, this is an isosceles triangle, and both of these end up being 17.6 meters per second. All right, the first one I'm going to focus on is the horizontal movement. This 17.6 won't change because it's not affected by gravity. And this is going to take us all the way up to our net. So we know the net is 50 meters away. So let's just do a distance equals speed times time calculation to figure out how long it's going to take to get there. So we need to travel 50 meters at a speed of 17.6 meters per second. How long is that going to take? Divide both sides by 17.6. And we get 50 divided by 17.6 is 2.85 seconds. So we've got 2.85 seconds in the air. All right, now we're going to figure out how high our daredevil is going to be at that moment of impact. So this was our work for the horizontal movement. Now let's focus on that vertical movement. So vertically, we start with an initial velocity of 17.6, an acceleration of negative 9.8. We know that we are going to be in the air for 2.85 seconds. We just don't know what our vertical distance will be. So I'm looking for the equation that doesn't have final velocity, and that is distance equals v initial times time plus 1/2 at squared. Let's plug in everything to that. Distance equals 17.6 times 2.85 plus 1/2 times gravity is a negative 9.8 because it's working in the opposite direction of our initial velocity. And then time is 2.85 squared. All right, plugging that whole thing into my calculator. And I get final distance equals 10.35 meters. And probably want to make sure that net is extra big to account for any air there, and he'll probably come in lower because of air resistance. All right, so that's that problem. On to our next problem. A ball is, I'm missing a word here. A ball is thrown straight upwards and returns to the thrower's hand after 3 seconds in the air. A second ball is thrown at an angle of 30 degrees. At what speed must the second ball be thrown so that it reaches the same height as the one thrown vertically? So we got to figure out how high up that first ball goes. Well, since it's thrown straight upwards, we don't have to really worry about vectors too much. Let's just break it down kinematically. So we know that the time is 3 seconds, but I'm actually going to just treat it like it's 1.5 seconds. All right, it's easier to just focus on the first half of this parabola from the moment it's thrown until it hits its highest point, and that's only 1.5 seconds. And then it's symmetrical, so that's why it takes 1.5 seconds on the way down. So the time is 1.5 seconds. The acceleration is negative 9.8. And then that final velocity, right when it hits its peak, is going to be 0. Can we figure out, we need to know the distance that it travels. So let's look for a kinematic equation that doesn't have initial velocity, and that is d equals v sub f times time minus 1/2 at squared. Now the final velocity is 0, so that term's going to go away. Distance equals negative 1/2 times 9.8 times 1.5 squared. And oh yeah, negative 9.8. That way the negatives will cancel out. Let me plug that into my calculator. 0.5 times 9.8 times 1.5 squared. I get a distance of 11.025 meters. So that's how high up the first ball goes. Now we have to throw another ball so that it reaches that same height. All right, and we are launching this one at only 30 degrees. That's a pretty shallow angle. It's going to be hard to get this all the way up to 11.25 meters. So the first thing I'll solve for is the vertical component of this vector. We need to make sure we pick a v sub y fast enough that it will reach 11.025 meters. So I don't know that the correct initial velocity, that'll be my question mark. But I do know the distance I want to go is 11.025 meters. The acceleration working against this velocity is negative 9.8 meters per second. And right when it hits the peak, my final velocity will go to 0. All right, so that I'll just barely reach that 11.025 before I have to turn around and start falling back down. So let's solve this for v initial. We need the equation that doesn't have time. So v final squared equals v initial squared plus 2ad. V final squared is 0. V initial squared is still unknown, plus 2 times negative 9.8 times 11.025. Multiply this together, and then we'll add it to both sides. So 2 times 9.8 times 11.025 gets me 216. So 216 equals v initial squared, take the square root, take the square root. And we get 14.7. So this velocity in here must be 14.7 meters per second. Now from that, can I figure out what this velocity is? So from that 30 degrees, I have an opposite. And I can solve for the hypotenuse by using sine. I'll set up my trig function like this. The sine of 30 degrees is equal to opposite 14.7 over the hypotenuse, which is x. This just needs rearranged a little bit. X equals 14.7 divided by the sine of 30. 14 look a little better. Plug that in. 14.7 divided by the sine of 30 gives me 29.4. So final answer, 29.4 meters per second, which is doable. I mean, that's like 70 miles per hour. You need a pretty good arm to throw that fast, but it is doable. All right, I know this is our first day of this, so keep practicing. I know you'll get better, and have a good rest of your day. I'll embed a few more questions for you to try here. Bye.